Hi there, I'm Matt Carter from the Sea Mammal Research Unit, and I'm going to be talking to you today about our project updating the at-sea distribution maps for harbour and grey seals in Scotland. There's been a number of various iterations of these distribution maps for seals in the UK over recent years, and the maps are widely used by developers, researchers and SNCBs for many questions relating to marine spatial planning, as well as conservation and management of seal populations. The most recent version of these maps was published in this paper in 2022, and it used a habitat-based approach to predict distribution. So briefly, in this framework, we use tracking data from seals tagged with ScotMER instrumentation GPS GSM devices, and we build a mathematical model of what characterises seal habitat use at sea. The models are fitted on a regional basis to account for geographic differences in the scale of movement, habitat features and diet, and predictions of distribution are then made using these models from each haul out around the coast on a 5-kilometre grid. These predictions are scaled according to the most recent August haul-out counts. So in other words, if there were 15 seals counted on a given haul-out, the model will then predict where these 15 seals are likely to be distributed at sea at any one time when they go on foraging trips. So the haul-out predictions are then all stitched together into one large map to give an overall picture of distribution. However, in this previous work, a key data gap was that there was a lack of telemetry data for both species in Shetland. As such, predictions for Shetland were made using habitat association relationships of seals hauling out in Orkney. And this was obviously not ideal, but at the time it was the best option available. Now, given that Shetland hosts around 10% of the harbour seals in the UK, this was a priority area for future tagging. So in order to address this issue and a number of other research interests, ScotMER undertook a large tag deployment on harbour seals in Shetland in 2022. In total, 29 ScotMER instrumentation GPS GSM devices were deployed in 2 separate areas of Shetland, corresponding to the 2 harbour seal SACs. So the map shows the tracks colour-coded by individual with black dots showing haul-out locations, and you can see that a lot of the data is concentrated within a couple of kilometres of the coastline. So the left-hand side shows southeast Shetland. There were too few animals in the Musa SAC to tag, so we had to tag elsewhere. And the right-hand shows Yale Sound Coast SAC. And this coast-hugging behaviour is presumably related to the threat of predation from orca. And this was the subject of a recent PhD project by ScotMER researcher Dr. Julia Sutherland. So stay tuned for updates from that project in the near future. So for this latest iteration of the distribution maps for Scotland, we pulled the new telemetry data from Shetland, highlighted here, with all existing data from seals that were tagged and made trips from haul-outs in Scotland. So this time the tracks are colour-coded by region, and these are regions that were used to fit the habitat association models. The count data used to scale the predictions were also updated to more recent surveys where available. And hot off the press, this is the first view of what they look like. The values show the approximate mean number of seals estimated to be in a 5-kilometre grid cell at any one time. And these maps are now available along with an accompanying report on the Scottish Government website. If you just search harbour and grey seal distribution maps for Scotland, you should come across it. So just to highlight the changes to predictions for harbour seals in Shetland specifically, a reminder that the previous predictions on the left used habitat associations of seals from Orkney, and the new predictions show a much tighter coastal distribution, and they were fitted using tracking data from seals tagged in Shetland. I just wanted to highlight a number of considerations when using these distribution maps. Firstly, the maps only represent distribution of seals making foraging trips from haul-outs in Scotland. So in offshore areas, particularly for grey seals close to the English border, this is likely to be an underestimate of total density, as it doesn't account for the overlapping of distribution of seals making trips from haul-outs in England, like the Farne Islands, for example. Secondly, the maps are relevant to the study season only. So tracking data were clipped to remove any potential breeding or molting behaviour, which could skew our idea of where seals are when they're foraging. So for harbour seals, the maps represent autumn, winter and spring, and for grey seals the map represents summer distribution. Next, the maps show a snapshot of distribution at any one time. That's to say that at any given point in time, if you drain the sea, you might have 5 seals in your particular grid cell, but those values don't convey any information about which particular individuals are using that space. And lastly, the confidence intervals reflect uncertainty in the mean estimate for the habitat association relationships only. So they're not to be used as upper and lower bounds for the number of seals in a given cell, just uncertainty around the mean. Okay, and I just wanted to flag some more relevant work that's in the pipeline at the moment. Scottish Government have funded a user-friendly app, which is being developed by Dr. Hannah Wiles and myself at ScotMER. And the seal mapping and analysis platform, or SealMap, will serve as a home for the latest version of the maps, where users can interact with the data and download the data. And it will also have this great new feature where users can upload a polygon for their area of interest, if that's an MPA or a development zone, for example. And the app then calculates the density of seals within that area with area-based confidence intervals. Importantly, the app will host estimates for Scotland, but also on a seal monitoring unit or special area of conservation level. So users can apportion at sea density to a given SMU or SAC. Okay, and under the EcoStar project, we've also been working on extending the seal maps to cover the Northwest European shelf by combining our data with data from collaborators across Europe. This will allow us to create a more kind of realistic estimates of seal density at sea and hopefully facilitate transboundary conservation and management. And lastly, I'd just like to thank you for listening and acknowledge our collaborators and funders on this work. And thanks in particular to all those people that have helped us in the field over the years, and too many people to list here. Thank you.
Good afternoon, everyone. My name's Joe Onofriu. I'm a senior marine mammal scientist with the Marine Directorate's Science, Evidence, Data and Digital Portfolio in the Renewables and Ecology team. And today I'm going to be talking to you about the Scottish Passive Acoustic Network, the current ScotMER funded project being delivered by the Marine Mammal team at Scottish Government. I'm almost entirely going to be taking credit for others' work in this presentation. The team of researchers you see here have jointly produced these results, and I will attempt to describe the projects and answer your questions after the talk as best I can. However, in many instances, we'll have to direct you to one of these brilliant people. The overall aim of this project is to build on existing acoustic monitoring projects to characterise understudied waters, provide baseline species occurrence data proximal to offshore wind developments, and estimate trends in cetacean occurrence and underwater noise profiles through the life cycle of renewable energy developments. The acoustic data for this project is collected using a suite of passive acoustic monitoring moorings at several sites across the Scottish coast. Each of these moorings consists of a station click detector and a broadband recorder. And in the interest of time, I'm just going to skip over the details of these, but please feel free to ask me some questions about them at the end of the session. In terms of the data currently held under this project, as I said, this project is an extension of the previous acoustic monitoring program, EcoMAS, which sought to collect data on cetacean distribution and ambient sound levels along the east coast since 2013. And these are all of these sites in green that you can see along the east here. Expand has extended this by adding an extra 20 sites that cover the north and the west coast, as well as the offshore regions on the east coast, and a further 2 sites up in Shetland. You can see these sites in yellow on this map. So on to some of the projects we're currently working on. I'm going to gloss over the statutory monitoring elements of what we do and focus on the discovery projects here. And so the first project we're going to talk about is being led by my colleagues Evelyn Philpott and Jack Lucas here at the Marine Directorate, and also to some degree by Chelonia. And the question this project is asking is, what are the trends in harbour porpoise occurrence across the east coast? And did the wind farm construction over the last decade cause them to move out of key areas? And if they did, do they come back afterwards? Now, these questions really were a key concern during the consenting for the East Coast wind farms, and one of the issues that is becoming very demanding during the HRA process. And it's really the reason the EcoMAS project was started in the first place. This project will primarily be using CPOD and FPOD data, EcoMAS sites, and the newly formed peripheral span sites are all going to be used to identify trends in both porpoise and dolphin occurrence patterns. Now for porpoises, the overall growth rate averaged about 7.9% per annum across all sites. There's a 2.2% average annual increase in the northern sections, whereas in the southern section, the growth rate averaged about 12.2% per annum. There's a clear coherence in the data with year-on-year trend profiles matching to some degree across both the north, south, and the inshore-offshore stratifications. There is also a correlation, albeit a rather weak one, between the patterns of trends in porpoises and dolphins. The trend patterns indicate that redistribution is a substantial factor, and that over the 10-year duration of the project, an average trend is beginning to emerge. Next steps are to correlate these trends with a suite of biotic and abiotic factors, including several environmental drivers, presence of assumed antagonists, dolphins in the case of the porpoise analysis, and factors describing wind farm activity for both construction and operational phases. Once models are finalized for the description of porpoise and dolphin drivers of distribution, noise analysis will be introduced in a further analysis using data from the broadband recorders to describe how changes in local sound profiles can impact cetacean occurrence. The next project I'm going to talk about is led by my unfortunately ex-colleagues Louise Wilson and Hannah Miller, and they are asking the question, how has ambient noise changed across the span sites through the study period, and what is the impact of wind farm development on coastal soundscapes? This project was centred around the Moray Firth, which hosts protected sites for both bottlenose dolphins and minke whales and coexists alongside significant anthropogenic activity. So the aim of this ongoing study is to investigate impacts of these activities on the soundscapes of coastal habitats across the Moray Firth. Moorings with broadband recorders were deployed at Lather and Helmsdale and Cromarty. Anthropogenic sound events linked to offshore wind farm developments during April 2017 and April 2019 were identified using the JNCC Marine Noise Registry and manual inspection of spectrograms. Power spectral density plots and spectrograms for each site were generated. Anthropogenic events detected at each site included boat sound, pile driving, and UXO clearance. Unfortunately, self-noise of the moorings used to deploy the equipment was detected at each site in 2017 and 2019, contaminating the recorded data between 0 and 2 kHz. The soundscapes of all three sites were similar in April 2017, with spectral grey values highest below 1 kHz and decreasing with an increase in frequency. Spikes in the upper percentiles in RMS level at Lather in April 2019 suggest increased boating activity at this site compared with 2017, and both years at Helmsdale and Cromarty. Anthropogenic activities in 2017 and 2019 were detected at all three sites, despite the furthest site being over 75 kilometres from these events. Further work is required to investigate the limitations and biases of mooring sound and clipped audio on the analysis of this dataset, which may lead to the effects of anthropogenic sound on the soundscapes being underestimated. While the implications of this work are currently limited in scope, research building on these analyses is warranted to better understand the propagation of wind farm construction sounds at distance from the source, and this could improve assessments carried out to predict the effects of these activities on protected sites, such as those in the Moray Firth. Final project I'll be discussing is led by my colleague Susanna Kerr and is asking the question, how comparable are archives of older data to newly collected data from different cetacean click detector devices? And this is quite an important question for our studies, as since 2020 we have started using the more up-to-date FPOD click detector, and while in many ways this is a superior device, we need to be able to quantify the difference in detection rate between the two devices so we can reliably use both CPOD, of which we have a lot of data for, and FPOD data in the same analysis. For porpoises, the correlation of detections between C and FPODs is quite strong. On almost 26,000 hours of data, there is an overall R-squared value between the two of about 0.95. This was much lower at some deployments than others, but this could be explained by either poor pod performance or some site-specific issues with detection during that period. Conversely, for dolphins, over 8,249 hours of data, the correlation was still relatively strong, with an R-squared value across all sites of about 0.81, but it was much more variable across sites, and there was higher variability in detectability between pods, especially when overall detectability was quite low. Overall, the identification of broad-scale daily occurrence patterns is minimally impacted, and this suggests that a simple correction factor could be possible for long-term analysis, especially for porpoises, as you can see on the plot on the left here. However, correction factors might be more difficult to apply to the dolphin data, as the patterns don't align perfectly as they do with porpoises. So that was a super brief and high-level tour of 3 of several projects that are currently being conducted in-house under the SPAN project umbrella. And I just wanted to quickly highlight some of the PhD and master's projects that are also using SPAN data at the moment, and highlight a few other projects that are currently leveraging our data for some applied projects. Just like to finally thank the ScotMER team for funding this project, to all the people that helped with fieldwork and data collection, and all the people that have provided advice on analysis over the last year. Thank you very much.
Hi everyone, great to be with you. Today I'll be presenting a piece of work called the RADIN project that was funded by the ORGIP program, administered by the Carbon Trust, all about trying to design offshore wind pile driving to minimize estimates of auditory injury. The work was done by a really big team. I'm the mouthpiece today, but I just want to acknowledge all the work from the team from ScotMER Consulting who drove a lot of this, and ITAP provided the data and a lot of the raw data analysis. So what are the most factors that are most important in PTS onset ranges? Typically, these are the largest ranges coming up in impact assessments for cumulative sound exposure. That's where they're coming from. What are the drivers behind that? Well, there are obviously physical elements, so the source level, the propagation conditions. There's obviously a lot of interest recently in the impulsiveness of the signal, and then things like the pattern of hammer strikes can make a difference in a cumulative sound exposure context. And of course, there's also biological elements. Responsive movement of the animal, the swim speed, the directivity of the movement, possible recovery of the hearing system, and then thinking about the longer term impacts of PTS on vital rates, whatever matters. And obviously in the UK, it's widely accepted that the animal shows adversive movement away from the source. So the way we attack this in the RADIN project, and I'm just presenting part of the RADIN project, you can find the report online, just search for ORGIP RADIN, and you'll find the report. This work part focused in on building an animal movement tool and some R functions in order to explore the factors that are most important. So drilling down into a bit more detail on those. It's built in NetLogo, and the way the tool works is that all the parameters are fixed for the duration of one simulation, but it runs very, very quickly. And so that means that you can do lots and lots of simulations over and over, investigating different factors, and really get through a kind of sensitivity analysis style effort. Ultimately, you've got a single strike SEL measured at each animat location, and then we apply weighting functions and can calculate the cumulative SEL. These are the variables that we currently have integrated into this tool, but we've also developed the framework. This was Magda Huzinska who developed it so that we've got a lot of potential to expand the tool in the future. So what factors are most important? So I'm going to show you some simulations where the source level was 220 decibels, we 1 micropascal. These are examples showing transmission loss of 17 log R, but these patterns hold over different source level and transmission loss setups. Obviously, the absolute ranges in terms of PTS impact ranges will change, but the patterns are what we're interested in here. And I'm showing you simulations where the duration of the simulations are 6 hours. So piling occurs for 6 hours and there's a blow every 2 seconds. So what we saw, and these different colored lines for low frequency and very high frequency cetaceans show that basically the changes in impulsive from impulsive to non-impulsive sounds needs to occur pretty close to the source within a couple of kilometers in order for it to make a meaningful difference. And probably what's most important and the biggest takeaway from this slide and these results is that it is the swim speed of the animals that are making the biggest factor. You can see if you look at the impact ranges on the y-axis, when the swim speed is 1 meter per second compared to 5 meters per second, or certainly the biggest changes from 0 to 1. So really any aversive movement can make a really big difference. And if we can determine that impulsiveness is also changed within the first 1 to 2 kilometers from the source, then this will also be a really important factor. And these simulations were really interesting for us. We just started with blow rates of every 2 seconds. We did some other simulations looking at changing that blow rate and realized that actually this was quite an important element. So because the project was funded by ORGIP, we had access to a lot of the developers who were very supportive of this effort. So we compiled over 200 real-world hammer logs from different wind farms around the UK and Northwest Europe. When we looked at all of those, we found that they were very, very similar, the vast majority. So we chose 44 that were the most different and ran them through the tool. These span a range of different pile diameters, and you can see these on the left. So time since the first pile strike is on the x-axis, and then the color coding is for different at different hammer diameters. And what you can see is actually the vast majority of cases are the piles are installed in about 3 hours. And at the bottom, I've showed this kind of simulated baseline. We reviewed 7 current EIA submissions and the kinds of piling parameters that are being considered by developers. And so this simulated baseline represents a good estimate of what's being put in impact assessments today. These hammer logs show how wind farms have been built in the last 10 years or so. And what's really been interesting is that we also saw within the first 45 minutes of the simulations that we see real variety in terms of what happens at the start. There's a lot of variability in terms of just how many pile strikes occur, and in the context of cumulative SEL, that's a really important factor. So we explored some design, so as the EIA is planned versus the real world, what happens when these things are actually built. These are simulations showing animals moving very slowly. We tried to be conservative. So animals moving just 0.2 meters per second, so about a fifth of how fast they're moved through in impact assessments, and then looked at the percentage reduction from this simulated EIA. So this black circle represents a kind of top view of the impact range with the hammer strike occurring in the middle. And then as we ran all these different simulations, we saw really pretty marked reductions. So the minimum reduction that we saw was a 16% reduction in the impacted area. The median reduction was 57% reduction in the impacted area just by altering the pattern of the pile strikes. And so we felt like this was a really, really important thing to better understand. And so we modeled this, and basically what we found was in the first 45 minutes of the pile driving, the longer the gaps between pile strikes, especially at the start, means lower impact ranges. And given the variety of what's been done here, it's clear that from an engineering perspective, there is some flexibility in terms of how these are installed. And we think this is a really valuable area to further explore, because we can argue about biological factors, but these are physical parameters. The pattern of hammer strikes is something that we can measure very, very precisely. And even as we've skewed quite conservatively in all of our assumptions in these simulations, we're seeing really meaningful changes just by focusing in on those hammer logs and really what happens when a wind farm is built and piles are installed, as compared to what's projected many years before with many assumptions in the impact assessment phase. So which factors are most important? Well, pattern of hammer strikes, the real world hammer logs really seem to pretty much have the impact, and in many cases more. And the number of blows in the first 45 minutes seems like a key area to advance. Of course, there are assumptions here on the biological side, but I think there's widespread agreement in the UK about the responsive movement. So the highlights and recommendations: important to utilize the evidence base to consider the assumption of no aversive movement. I think that's important. Clearly, swim speed matters. So getting those swim speed estimates right is an important one. But these results are all still quite conservative and can be improved. We've skewed very conservatively on most of our assumptions, and so the real world impacts may be even smaller than what I've shown here. There may be more things to reduce when you consider things like ramp up and other factors. Making sure that we haven't just got a biased 200 hammer logs would be good. So perhaps doing a census of real world hammer logs and comparing them to EIA assumptions would be valuable. And then because we've found that there's real scope to reduce impacts in this kind of primary mitigation, so designing this into the project, there could be real scope to reduce impacts by increasing engagement between what's possible from engineers, what regulatory advisors are comfortable with, how the acoustics fit in on the marine mammal side, and explicitly design hammer logs that can minimize impact ranges. Thanks very much.
Good afternoon. My name is Nuria Abad, and I'm the Offshore Consents Manager at Ocean Winds. During this presentation, I will provide the evidence demonstrating that the use of low-order deflagration technique mitigates UXO clearance noise, and how this evidence can now be used with confidence to minimize precaution in impact assessment, licensing application, and more sustainable UXO clearance. Firstly, offshore wind farm sites often overlap with areas previously used in military conflicts and practice sites. Therefore, it is not uncommon to encounter UXOs in the marine environment, which poses a risk not only to offshore infrastructure, but also to other sea users and marine fauna. In the UK, the use of explosives at sea is a licensable activity, and UXO clearance operations must be licensed and managed to minimize impacts in the marine environment. Most importantly, underwater noise impacts on protected marine mammals. UXO disposal operations have traditionally been undertaken by high-order detonation techniques, using an additional high-explosive donor charge. However, in recent years, offshore wind developers and their stakeholders have recognized the need for alternative methods of UXO disposal to reduce environmental impacts, such as low-water deflagration, which results in the explosive content within the UXO being rapidly burned away rather than detonating. Today, I'm presenting the outcomes of the first large-scale commercial use of the low-water deflagration disposal methodology during the UXO clearance prior to offshore construction of the Moray West offshore wind farm, located in the Outer Moray Firth in Scotland. During UXO clearance operations at Moray West offshore wind farm, low-water deflagration technique was used by EODX to successfully clear a total of 82 UXOs of different types and with a wide range of explosive content, from 6 to 700 kilograms. Disposal tool charges that are required for low-water deflagration were between 100 and 250 grams. Overall, a total of 28 kilograms of donor charge was used to safely dispose of all UXOs. In comparison, traditional high-order detonation techniques would have required between 5 and 10 kilograms of high explosive per UXO disposal and used between 830 and 2075 kilograms for the same number of UXO disposals. Additionally, majority of the UXOs only required a single deflagration attempt to be safety neutralized. In order to quantify the reduction in underwater noise levels resulting from low-water deflagration compared to high-order detonation, noise measurements were made by SAGE on a representative sample of 31 UXOs at different distances. This slide presents a summary of the noise monitoring results. The graph in the slide shows a comparison of model noise levels for the disposal tool charge size of 125 grams and a UXO with an explosive quantity of 700 kilograms against measured receive levels for all UXO clearance attempts for the LNB mine at 1, 5, and 10 kilometers. The top line shows model received noise levels for the clearance of a UXO target of 700 kilograms. The bottom line shows the modeled received noise levels for the clearance of a disposal tool charge of 125 grams. Measured noise levels at 1, 5, and 10 kilometers are represented as X's. Overall, the results of the noise monitoring of 31 UXOs highlights that the measured noise levels fell consistently below the model noise levels for the disposal tool charge and for the disposal of a UXO target of the same explosive content, which indicates that none of the UXO underwent high-order detonation. And although underwater noise is still being produced, the results are showing that this is governed by the disposal tool charge of known size, as opposed to the explosive content of the UXO. The maximum measured noise levels resulting from low-water deflagration, which were recorded at 1 kilometer from the UXO, are significantly lower than expected had a high-order detonation had taken place. In summary, the results from the noise monitoring demonstrate that low-water deflagration techniques can be practically deployed in the marine environment, reduce underwater noise and the risk of injury to protected marine mammals. It also demonstrates that future noise modeling can be accurate and reliable by using known disposal tool charge sizes. Moray West case study demonstrates the efficacy of this methodology to clear all types of UXOs while simultaneously reducing environmental impacts associated with UXO clearance, not only underwater noise, but also the lack of seabed disturbance, for example, the creation of craters. As observed in this slide, there were no visual seabed craters or disturbance resulting from low-water deflagration. Additionally, all UXO debris was fully removed from the seabed following disposal. And although a small percentage of UXOs required more than one deflagration attempt, we can certainly confirm that none underwent high-order detonation during the disposal operations. To conclude, the outputs from the Moray West case study should be used to streamline and facilitate the licensing decision-making process by, firstly, reducing uncertainties over the impacts associated with UXO clearance, minimize precaution in future impact assessment and license application, Noise modeling and impact assessment for UXO clearance by low order deflagration should be based on known and small disposal tool charge size rather than less certain and often large estimates of the UXO explosive content. And develop appropriate and proportionate mitigation measures for the UXO clearance. We believe that these changes in the approach to licensing and clearance of the UXO could reduce uncertainties in project timescales and prevent delays in consenting and delivery of renewable targets. Sharing evidence to improve our knowledge on novel technology is key to progress with the growth of offshore wind, while reducing conservatism and minimizing the impacts on marine wildlife. OW have published the findings of the Moray West case study, hoping that this new evidence will lead to streamlined licensing and decision-making process for future UXO clearance and adoption of low-order deflagration techniques by other offshore wind developers. Thank you for listening, and please do not hesitate to contact me if you have any questions.